All right, folks, I am back, and here we go, continuing with why certain elements are very reactive or very eager to bond, that is, to gain or lose electrons. Now, if we talk about the elements over here on the left side of the periodic table, we would say that they have valence electrons that are easy to remove, and that makes them highly reactive also. If things have a low number of valence electrons, it's very easy to remove those valence electrons because the atoms would be really happy if they can get to 8 is great. They only have 1 or 2 valence electrons. They're going to just lose those very easily, and then it will make them stable. It will make them more like a noble gas. So we would say that these elements have very low first ionization energy. You don't have to use much energy to pull off 1 electron or 2 electrons if those are the only valence electrons that the atom has. Now, one additional idea is that valence electrons that are further from the nucleus are easy to remove. We already talked about the idea that the positive nucleus holds onto those negative electrons, but if there are more shells, it's not as easy for the positive nucleus to hold onto those negative electrons. The idea of the nucleus being like the guard, the electrons are like the money, and as the electrons are further away from the guard, it's easier for them to be plucked off by other atoms. The way chemists talk about this is that the shells are like shielding. Okay, as you get an element with more and more shells of electrons, those electrons that are on the outer edges are shielded from the positive pull of the nucleus, and so it's not as easy, or excuse me, it is much easier to pull those electrons off if they are further away from the nucleus. Okay. Yep, that is it for today's review of some periodic table patterns. Now I just want to add one new topic that is kind of getting squeezed into this unit. And if you turn to page 51, we're going to talk about what is an allotrope. It's kind of like an isotope, but the word is allotrope. So turn to page 51. Hit pause if you need to. Okay, the definition of an allotrope. It's something where you've got a situation where it is the same element, but has a different molecular arrangement or structure, which gives it different chemical and physical properties. Okay, so things can be the same element, but if they're arranged in a different molecular structure, that will give them different chemical and physical properties. Now, you can maybe predict what I'm about to say about carbon, because I know you've heard this before. Carbon can be in the form of diamond. Diamond is pure carbon, but pure carbon can also be in the form of graphite. Now, diamond has a certain molecular structure or arrangement. Graphite has a different molecular structure or arrangement. It's in these weird sheets or layers. And we also have another form of carbon, pure carbon, that the shorthand name for it is buckyballs. These types of carbon were discovered in the 1960s by a guy whose name was Buckminster Fuller, first name Buckminster, last name Fuller. So the technical name of these is Buckminster fullerenes, these type of compounds, but people have tended to call them buckyballs because they often have this spherical shape. Now, diamond has certain properties. It's incredibly hard. Graphite is a very weak element, but it makes a great lubricant because these layers slide past one another. Powdered graphite, you can puff it into a lock, and the lock will work much more smoothly if it is jammed up a little bit. Buckyballs are pretty weird and interesting. They're very non-reactive, but they have very interesting properties of electrical conductivity and heat conductivity. So again, they're all carbon, but because of their different molecular arrangement, different molecular structure, they have different chemical and physical properties. Here are a couple more examples. Phosphorus can be P4, which is white phosphorus, or just plain old P, which is generally black phosphorus, and then there can be P8, which is red phosphorus. They are all the element phosphorus, but they have different properties. Particularly, you can see that, they have different colors. That would be a physical property. There also is violet phosphorus, and I don't know too much about it, but it is another allotrope of phosphorus. Now, oxygen you should be familiar with. O2 is oxygen gas, and O3 is called ozone. Now, O2, you know that that's very good for life. Organisms need oxygen for respiration. O3 is bad for life up close. ozone molecules will do bad things to cell membranes and rip them apart. Ozone is really, really good and important in our ozone layer, way up high in our atmosphere. It protects the Earth from ultraviolet radiation. But up close, O3 tends to rip apart cells and cell membranes, so it's not good for living things. Don't breathe in ozone, kids. So again, they're both oxygen, but in different different structural arrangements, so they have different chemical and physical properties. All right, that's it for allotropes and for this lesson. Thanks for watching.